Hello and welcome. Here we are in lecture 14. So today we're going to talk about inheritance. So as a reminder, this is yet another set of Scala functionality we're using to make more usable, more parameterized chisel code. So if you remember how we kind of been going about material in this course, we've been kind of covering something and then perhaps a little bit superficially and then going back to it in more detail. So that's what today is. We have talked about classes so far in this course. We talked about various types of reuse. Even mentioned there's multiple kinds of classes in Scala. And so today we're going to come back and talk about some more of those kinds of classes and how we can use them within our chisel designs. So specifically, we're talking about how to do inheritance with object-oriented programming in Scala, how we should apply that in our chisel designs. We'll talk about type parameterization, which is something we talked about briefly at the end of the last lecture. Oh yeah, we built this nice parameterized Q class, but we're still stuck with uint. Can we somehow be more flexible? And then finally, I'll give a brief overview of the class project, and what's going to be doing the remainder of the quarter after the homeworks. So let's go ahead and load things up. Hopefully take some seconds. Here we go. Okay. So the big question is why am I talking about this? Well, the whole goal is reuse, right? The reuse in general has two big purposes, right? It's not just a matter of taking someone else's code, and because you didn't write the code, you save time and it's much more productive. When you reuse high quality code, it also helps you reduce errors, right? Because hopefully it's already been debugged and tested. Hopefully, not guaranteed, of course. Um, so the goal of the course is to have things be more reusable. And it turns out we're doing hard design. Most things we're building aren't that unique a lot of the time. At least some component of it's not that unique. And so the parts that aren't unique or aren't novel for what we're building, we might as well try to use this as much as possible, right? So um, that's kind of the goal. And so object-oriented programming is going to be yet another tool we're going to have to try and make things more reusable, right? So we talked about, oh, well, parameters and generators. Inheritance is another way to kind of get a little bit more flexibility, a little bit more reuse, right? And so in particular, where is inheritance most useful? If you have different components, but they behave similar in many cases, you could choose to have perhaps like a Boolean flag or some sort of parameter that makes the generator behave differently, or perhaps actually having different classes exposed to the user, different modules exposed to users is best, but actually you share some code internally. Uh, or alternatively, you can have the same interface, right? So we'll see kind of both of these come today. And so Scala is really, really excited about inheritance. There's a lot of different classes. As we've joked in this course, it's a rich language. There's always, more features to be learned. So we're only going to cover a couple of the class mechanisms today, but there's far more you can read about. Okay, let's go ahead and get to it. So as we discussed before, right, you can define a class in Scala with the class keyword. The arguments used to construct it are always the same. This body's evaluated when it's created, and then of course we talked about things like objects and companion constructors last time. Not worrying about that today, but in this example we're going to do it in case of inheritance. So we go ahead and define a parent class, and so without maybe temporarily hiding this, we go ahead and run this, right? Yes, we can instantiate Kate of a parent, and so yeah, our class given a name goes ahead and greets that person. Okay. Now for the child class, the way we indicate we're doing inheritance, of course, is the extends keyword. When we create the parent class, we also need to give it its arguments. In this case, we're actually reusing the same argument from here and passing it on up to the parent class. Then inside the child, of course, if we did nothing different, that's totally valid. However, it doesn't only get as much, right? We have a different type, but it's going to behave exactly the same. So Pablo's going to still say the same thing. However, if we decide, we actually want to do inheritance and do something different in the child class, we can go ahead and override the behavior in the parent. In this case, we're going to change our greeting phrase. So now we get hola Pablo, right? And notice what's happening here. When we call child, we create a child, okay, great. And we call greet, it looks in the child context, can't find it, goes to parent context, evaluates this greet method. And while evaluating this, it actually gets the phrase from the child class, right? So, we're calling code from both places. It's going to try, closest to where we called first. So start from the child, and it can't find us, keep going up. And it does it for every single thing it looks up, right? So in this case, it looked up phrase and it found it in the child, so it used that one. So that's why I was able to override it. But the key point in this case is now you can imagine with a little bit of changing, we're able to, In this case, we use a discrete function across multiple classes. Yes, question. I believe it's required. Let's see what happens if I remove this override keyword. Correct. So that's actually a nice feature, right? So basically, you need to be very sure about what you're doing. Now, if I create something new that's not in the parent class, that should be totally be fine, right? VP2 equals something, that shouldn't care, right? But yeah, if there's a field that's in one of the parent classes, you need to explicitly say override. That's kind of you confirming, yes, I know what I'm doing. It's not just a coincidence, of us choosing a very common name like define or name or something. Cool. Okay. Let's keep going. So that was, traditional class inheritance. Um, Sometimes you want to use what's called an abstract class inheritance. So the only difference is not so much in the inheritance portion, that's the same, but the actual parent class is different. So it's an abstract class, meaning it cannot be instantiated, right? That's the key rule of an abstract class. So you can define a class. If it's abstract class, you can put things inside. You can put methods. You can put feature. You can put fields. But you cannot instantiate abstract class directly. You can only instantiate children of it, right? And so there's children that implement an abstract class are called the concrete classes, right? And so in this case, for example, we define an abstract class, same as we did in the last slide. We just added the keyword abstract. And now we can go ahead and make child classes, just like before. And yeah, and in this case, we have these two child classes. So you may be wondering, what's the advantage to an abstract class? It's one of these tools you have in your arsenal of options when you're starting to build up your class hierarchy. So when you're thinking about how you want to use inheritance for your generator, or in this case, perhaps a generator library, multiple different types of generators, if you're thinking about how certain things are reused, this is another tool you have in the toolbox. So what's the trade-off of abstract class? The trade-off is it's something they can, more easily kind of get out there, and you can kind of clarify things. This is kind of an idea, but it shouldn't actually be implemented. And so that constraint actually is kind of nice, where you can kind of have some functionality in there. You don't need to worry about thinking all the way through. You can do it kind of, as the name implies, in the abstract, and then leave it for the concrete classes to kind of do the rest. And so if you see, for example, here we define the field phrase, and because it's an abstract class, we actually didn't give it a value, which is kind of crazy, right? Because normally when you see val, you kind of, it's right once, right? So it's immutable. You can't change it. Here we define there's going to be a val phrase, and we don't give it a value, and then the concrete class is able to, set the value. Now they aren't overwriting it. It never had a value, right? It's just here it's defining, and here it's actually setting the value. Now, one thing people often ask about object inheritance in any language is, oh, can I do multiple inheritance? Can I, extend multiple classes? And so there's a variety of challenges that come up with this problem. We made for something called the diamond inheritance challenge, where if you have, common ancestors, what happens? Scala's solution to that is that you actually only inherit from one class. Could be abstract, could be not abstract. You only can extend one class. So you're like, wait, what if I somehow want to mix in more things? That's where you use what they call mixins, which are done with this trait keyword. So we'll see traits in a few minutes as another way to kind of do this. So you can see there's a lot of options for classes in Scala, but maybe I'll pause here for any questions so far. Yes? What would happen if I did var phrase here? Let's find out. It's probably going to complain. Yeah, okay, so it recognizes that this does not match the same as over here. This is probably going to make it more okay if I make them all var, right? But yeah, so they need to match up. Yay, cool. So this is the part of Scala mentality, right? Do whatever we can in the compiler and the type checking and such to prevent things that should be errors. Occasionally, there's things that aren't errors, like we saw in the prior one. We really want to override phrase. Here, in the case of the abstract class with the child classes, right? They aren't overriding phrase; they're just defining it. It's actually just specced out, but actually there's no value to it. So they didn't have to use the override keyword here because it wasn't needed because it's already an abstract class. And I'm curious if I was to do that, it would be okay with it, right? But it's because it's an abstract class. You have to fill in those fields anyways. Cool. Yes. Am I required to override these fields? I believe so. So if I leave out phrase, it's going to say, yeah, this is this class needs to be abstract as well because it does not fully concretize, all the things inside of it. It's a good question. Okay, cool. So here we're kind of playing with these various Scala class constructs. Uh, so it's something we kind of talked about in passing during the term. It's worth looking at concretely. Here is the type hierarchy for Scala's collections, right? So we've been using these all quarter. Particularly, I've often been saying, oh yeah, let's use a seek, right? Perhaps at some point you use some of these other collections or something, right? And you often saw, when it made concrete types, it often used, a vector or a list. So you can see that these blue types are abstract, right? They actually don't exist. You can't instantiate them directly. However, it's more than fine for us to, declare them, and then the compiler when it runs and go ahead and actually use a concrete type in its place. And so what's nice about that is we can say things like, oh yeah, my code works with seek, and by working with a high-level class interface, right, all these different classes which have very different internal implementations are still compatible. It's the same API, same interfaces, same types, right? So you can imagine, of course, the internals of a vector or numeric range, or even a string, of course, are pretty different than like a stack, right? So that's cool. But what's neat is you kind of recognize when you build a type hierarchy, you're trying to figure out what makes things similar, what makes things different, right? So you see, for example, that all of these things here are seeks, right? Sequence, as the name implies, right? And it's just a collection of elements with some notion of an order, right? It's kind of what the seek uniting trait is, right? And then whether you can do random lookup to it or you can only do linear, basically streaming in or out lookup to it, so it's the linear seek is versus there's some other collection classes, right? There's, sets. Okay, everything needs to be unique is kind of the key trait they're capturing. Or what about a map, which can have more arbitrary mapping functions in the sense of, you could have identifiers perhaps that are strings or something, mapping to some sort of result, so like a hash map or something. And if you ask me the difference between iterable versus traversable, I'm going to get it wrong. But basically, it's, as the name implies, it's something that separates those two things, right? Something you have some collection, there's some way to kind of traverse them all. That's a detail. Amusingly, I believe for Scala 3, they're actually combining traversable and iterable. I think someone decided that distinction was not worth it. So that gives you a sense. But this is just the immutable collections. The reason why I showed this is kind of give you a sense of you can kind of start thinking about a more rich library of components. Perhaps aren't just different components, but actually they should have some sort of overlapping and sharing of traits, right? And realize in this case, right, these are collections, right? So all these things are designed to hold multiple elements of some type, right? And there's different traits, whether it be certain key properties, right? So for a set, right, the properties everything's unique. Or for a seek, the properties are some sort of order associated with it. Or a map, it's just having some sort of arbitrary mapping type to one to the other, right? So you kind of see these kind of key properties kind of keep in there, and you can kind of overlap a lot. What's nice is you do this right, you can put a lot of code, for example, inside seek, and then the other stuff kind of does the right stuff. So for example, maybe when you do, dot map, for all you know, the implementation for dot map could be inside iterable or traversable, right? It could be much higher up, necessarily inside of an vector. But if vector wants to do something unique, it could. But if it doesn't need to do anything unique, perhaps you could do it more generally and you kind of get that reuse. Cool. Questions? Yes. Yeah, the question is, what about the arrow thicknesses between single width, double width, and dotted? I forgot. We can go to the documentation page and see if they tell us. Otherwise, I've forgotten in the sands of time. Oh, here we go. So you can see the various types of extension, right? So whether it's the default implementation, which we're talking about, like for seeks, we often get pulled into like, a vec, right, for example, or your traditional inheritance or implicit conversion. So it's something that's possible in Scala, right, where sometimes there are situations where you want to extend a class and you can extend a class without modifying. Sorry, you can extend the class, but the result looks like the original class has more functions than originally. That's what the implicit class lets you do. That's what the implicit inheritance lets you do. So I'm not going to cover it on this class, but I was saying that in passing, so I can mention it again. Something called an implicit class in Scala where you can It's like you take a class that exists, you extend it, and because you've extended, you can now add functions to that. And so for the functions you've extended, you have those new functions. And so instead of having to always call this new class and then count out by default going back to the original class, you can use implicit classes to make it look like the new functions you defined are always on the original class. But yeah, you can kind of see like the common paths, right? So in our class, we often see list and vector. And well, depending on how we use the seek, if we have to do indexing versus just iterating it, we get either a list or a vector kind of chosen by the default implementations. Or a vector, depending on how you're using it. Yeah, so if you instantiate a seek, depending on the way it's used, it's going to be either a list or a vector. So let's go ahead and make a really quick code snippet. I think I can show this, right? Or maybe use one of a smaller code block. So for example, val s equals seek of 1, 2, 3. And maybe I'm going to temporarily cut this. We can get the window back. Okay, we get a list, right? So that's just like that. Now, if I say s of 0, so I'm accessing this, it should probably make this into a vector. Or maybe not. I'm not sure which conditions create a vector, but we've seen it a few times in this course. You're right. So in this case, it's going to be default by list. I'm not sure the conditions that cause a vector, but we've seen it happen a few times in this course, and I've also lost my buffer. There it goes. That's a good suggestion. Yeah. Okay. So what if I define a seek and do more general accesses, perhaps? This is not the way to iterate this, right? But we're going to do it anyways. Oops. And then I say, print line, s of I. Okay, but we have seen a vector. I'm not crazy, right? We've all seen it. It's a vector in the room right now. Apparently it's not, but we've seen it though. It's been here before. Um, but that's kind of the point. So you can kind of see that. And like I said, so the suggestion from style guys nowadays is to use concrete classes because there are significant performance implications depending on which one of these types you use. I continue both, not just Chisel code, but the Scala code we use to manipulate things in CAD tools. You use seek because it's just simple for everybody to kind of think about it rather than converting types. And at least we're making hardware generators. Usually you don't have seeks that are very big, right? You don't have like a 1 billion element seek, right? So it's not so impactful. So great questions. Cool. Um, so that was kind of the whirlwind tour of the features in Scala. So let's try and apply these to Chisel, right? And so I mentioned this earlier and kind of come back to this, right? We've been doing different types of trying to get reuse, right? The whole goal is to get productivity via reuse, and so there's different ways. So number one, parameterized generators, right? We can take numerical parameters, booleans, whatever, and based on how generator is written internally, you can do a lot, right? A lot more flexible than just having a single instance, right? The generator is pretty cool. We also played around with bundles, right? And with bundles, we could do things like even optional ports, right? So that was pretty cool. We could have vecs of arbitrary sizes. So there's some ways to kind of have some parameterizability, some customizability there. And so with inheritance today, the goal is so much more flexibility. The goal is actually to implement flexibility with less repetition, right? You can imagine wanting to build a library of generators, and these generators are similar but different. Without inheritance, you kind of need to implement them all over and over again. And perhaps when you're writing them, you might be tempted to like copy paste one, start the other one. Whenever you're programming, you find yourself copy pasting code that should be a sign of repetition. And even though it's tempting to do it in the moment you're doing it, it's usually a sign you should do refactor and figure out a way to share things. And so one nice way to share code and reduce the repetition of having this larger library of components is inheritance, right? And so we're going to kind of see this in a few different places. And so we're going to use inheritance to try and hopefully build up, more robust libraries of components. But inheritance is also possible to do things like Chisel itself, right? Chisel itself makes ready use of inheritance where we have this kind of illusion of writing this DSL called Chisel, and a lot of it's powered by the fact that we are extending classes they've already created, and that's kind of the mechanism we're kind of using to build this DSL. Okay, so let's see a module example of this, right? So as discussed before, when you send modules, technically you're already inheriting. You've been doing it all quarter. But let's look at an abstract class, right? Our abstract class will be a unary operation, right? So we're going to go ahead and say it has some sort of operation it performs. It takes in a uint, produces a uint, and sure, we can have an IO for it, and yeah, we'll apply that operator to it. And so you can see an example, given this abstract class, we can kind of share some functionality. Now we can define these library components much simpler, right? We can just say, hey, give me, this pass-through module. We're extending this abstract class, so nobody can implement, so nobody can instantiate this class because it's abstract, and it doesn't make sense to instantiate it because it's incomplete, right? There's no type in there, right? And so there we can have these various cases, right? Pass through, we do nothing to it, we can negate it, and yeah, of course we can generate Verilog. We've seen this all quarter. It runs. Okay, yeah, we can do nothing, or we can of course negate it. Sure. So yeah, this is pretty cool, right? So we can do this. And so you may be asking, okay, well, what's stopping me from saying, you know what, I didn't want this to be abstract and I just want this to be class? Well, you need to have a fully defined class to not be abstract. Okay, well, what if by default I just did nothing, right? That should still be okay. Oh, now I need to override because it's not abstract anymore. So this is also possible. So let's kind of compare these two real quick, right? So why was the abstract class better here? Number one, uh, this is kind of giving a preferential conceptual treatment to notion of being a pass-through object, right? Which is sometimes when you have a library components, there's a clear base class and extensions of it. Other times conceptually, these things are on equal, peers or equal ground, right? So in this case, we consider pass-through and negation both equivalent. So we don't want one to kind of be a default, the other one kind of being different. They're kind of both equivalent, kind of a better conceptual understanding of what's going on. Also in terms of declaring things, right? Okay, you can keep overriding things or you make it really clear what needs to be done, right? So it's really clear what needs to be done if we have an abstract class, right? And so it's like, okay, this thing's not fully instantiated. I need to extend that, make that really clear, and then it kind of comes out. Cool. Questions? Okay, so let's go ahead and see some other examples. Let's say we're going to try and build something a little more sophisticated. In this case, we're building up another abstract class. And it's going to be a bit more sophisticated. So I'm calling this a decoupled operator. So what does that mean? It's something that takes in two arguments this time. So now it's a binary operator. And both inputs are decoupled and the output's decoupled. So the idea this is going to work is if you give me if both inputs fire and I'm empty, I'm going to go ahead and perform the operation and store the result inside an internal buffer. And then if someone wants to read my buffer, they can do that decoupled on the output. So we have decoupled inputs, decoupled outputs. If we have room, we can go ahead and fire the inputs, and the inputs are available, we can go ahead and fire. So this is perhaps not different from the Q stuff we were seeing in the last lecture. So we can go ahead and define this decoupled operator. So here we have all this code, but now what's cool is we're going to build up a library components, right? So we can do multiple things. We have an add, maybe a subtract, and so these two modules without inheritance would be way more code, right? It would be basically the prior slide. You can imagine you'd have very redundant code, right? The only thing that differs between those two modules is basically just one operation, right? The other, 22 lines, 24 lines would be the same. And so why not capture that with inheritance, right? So we get that reuse. So we can define this once, and then, let's say I want to change some of the handshaking from my library. I change it here, and it applies automatically to all components, right? So it's kind of a very good use of reuse. Don't repeat yourself, right? It's kind of the whole classic software engineering principle, the dry principle, they call it. So neat. We can have, an add, a subtract, and like before, we could even go a step further and have a companion object, and even have a return with a factory method to return what we want. So in this case, we're actually taking in a string for the operator we want, and it's actually returning different class types depending on what we're doing. Now, what's interesting is we're actually able to return the type of the parent class, the abstract class. And these are actually specific concrete classes. So that means that people elsewhere who use this code, depending on how to write in their code, they can, of course, be sure to gain a decoupled operator. But if they want to have the specificity of saying it's a decoupled add, they can do that too. Cool. So go ahead and run a quick demo of this, right? So we can go ahead and, See the object, right? It's a lot of stuff, but the kind of key thing is in the middle. There's the add. First, we want to do a subtract. You can do subtract. Um, so you can imagine it's not too hard to kind of build up these kind of libraries this way with inheritance and kind of build components. And so, yeah, here we have the Verilog. We also can do a demo of it executing a trivial execution. Actually, subtract maybe is not the best one to use for that one. Oh, fortunately, it's still plus. Oh, great. So the test case is taking the current cycle number plus one, and feeding those into two inputs. And because it's decoupled, it's not guaranteed to go in, right? So we're looking at the output, and if it's valid, so you see, oh yeah, eventually 0 plus 1 is 1. They try to go in next cycle, it's still busy. Then it goes in the cycle after that, it's available. So you can kind of see it progressing through it. Because of the way we have decoupled on both sides, and because we don't have this like pipe feature we're talking about for queues, you kind of can only produce a result every other cycle in the best case, right? So it's kind of that, that bubble. But if you allowed it to continue to fire when it's guaranteed to pull, you can, of course, get that fully utilized. But the reason why I did this is to kind of show the benefit of having this, right? We can just have a factory method quickly produce things, and these components, have nice, concise implementations. The things that makes them different is concise. And then we have it like this, right? And so you may remember in the very beginning of the course, we were doing a lot of stuff where we had like, a Boolean parameter. And if that was true, we could change stuff internally. We could have done that here, right? You can imagine, oh yeah, if add, do plus, otherwise else do subtract, right? But this is actually better, right? Because this way now we have different types. And you start looking at the fertile, the Verilog, etc. You actually can tell which one's which from apart. And let's say someone else, like I said, someone else wants to depend on it being definitely the add version as opposed to not the subtract version. They can require that specific subtype. And if it doesn't match, it's going to flag a compiler error. So yeah, so it's kind of cool. So we're kind of getting a little bit more types in our world to get more compile time checks. It's kind of these advantages we're doing. Cool. Questions? Okay. All right. Well, let's keep going. So the third Scala inheritance thing we're talking about is a trait. So let's kind of recap what we talked about so far. We're talking about regular class inheritance, which, as I mentioned, we're doing all code or not even thinking about it when we make modules and such or bundles. Abstract class inheritance, when you know for sure you want to have this, shared abstract parent class. But you're not required to. You can do inheritance without it, right? And then here's what's called a trait. So what's a trait? A trait's kind of this thing where it's like overlaps functionality of abstract with some key differences, right? So you cannot instantiate a trait. So whoever wants to use a trait has to inherit it. However, what makes inherit a trait cool is that it's designed to be multiply inherited, right? You can inherit multiple traits and it won't complain. So maybe wondering why is that such an important distinction, that subtle difference of I can inherit only from one class, whether it be abstract or concrete, but I can inherit from many traits. So the reason why traits are kind of cool like this is there's a few things about traits that make them able to do this. One of the key things about traits is that they don't take constructor parameters. And that seems like a really subtle point. But because of that restriction, that constraint on them, it actually makes it easier for the Scala language designers to resolve a lot of these classic object-oriented challenges of multiple inheritance. And so a lot of those challenges have been sized up by that small tweak. And so when people use traits, sometimes call these mix-ins, as in you're mixing in functionality. And so that's the kind of idea. If there's some functionality you want to have and you want to just kind of add to an object. So rather than doing a full-on new class, new type, I just want to have maybe a certain interface or a certain API. That's what you use a mix-in for. And so people actually use it in Chisel all the time. You can imagine you could have a Chisel module, great, does what it's doing, and maybe make a mix-in trait for JTAG debugging or something, right? And so you can just mix that in, and now, boom, you got JTAG in there. And you don't need to worry about doing anything else. So that way, for example, in your top-level design, yes, you have to keep wiring up all these JTAG wires and all these IOs and stuff. This happens kind of under the hood automatically. So we're going to see an example of that in my next slide, but it's not quite as sophisticated as the JTAG thing I just pitched. So let's say you're doing debug, right? So here we have this trait, which we are going to allow somebody to poke a module. And if poked, it will print a message. So of course, this only works in simulation. You can't do this in hardware. There's no printing in hardware. But let's see how this plays out, right? Okay, so number one is a trait. So there's no Constructor parameters. Okay, now we have our actual module. And so when you're doing traits, you don't say extends, you say with. So now we have print and sim. So basically, this has been injected into here. And so like an abstract class, a trait can have some things defined, but not fully, described, right? So yeah, we say we're gonna need a message. We get the message from our, actual concrete instance. And so now this actually is adding IOs to our design. So our design originally only has an IO for the output, and we call it out, sure. And then because of this trait, we've now added an input called print enable. So you can see now in the tester, we can go ahead and poke this, right? So initially, we poke false, so it's not going to print, and then we poke true and it does print, and yeah, we're printing it for 2 cycles. But that's pretty cool. Now, one small detail maybe you picked up on is we didn't extend module. We extended multi-IO module, right? So normally for a classic module in Chisel, we recommend extending module. You need to have an IO type, an IO field. That's kind of one of the ways of making sure you're like following this abstract class correctly, right? Making sure you're doing the right thing. You have IO defined, and you expect IO to be there. And we think when it comes to code readability, having IOs be prefixed by IO makes it really clear for somebody, oh yes, this is a IO thing as opposed to an internal field. That being said, Chisel provides this class called multi-IO module, which has none of those requirements, right? You can have IOs not from the IO bundle. You can have multiple IOs as the name would imply. So you can see in this case, the user is able to define their IO, and they give it any name they feel like, and they chose out. And then this trait, which mixes in stuff to your class, can also define its own IOs. And so, for example, if what you're doing with traits requires additional IOs produced by the trait, you're going to need multi-IO module. Not required. You can do stuff with traits and mix-ins that don't need a multi-IO module, but in this particular case, it does. So this is one of those things that kind of helps out, where you can imagine from a point of view of code maintainability, if you have something like, I mentioned debugging or JTAG or something, and you don't want it to kind of keep pasting code or modifying all this, yeah, capture that key common functionality you keep reusing, put that into something. In this case, we're putting that into a trait, and so that way you can kind of see we're not creating a parent class. We're creating this, trait and these aspects, these mix-ins, we're going to go ahead and use in other places. Question, yes? Yeah. Yeah, the question is, can I have bundles here? Yes, you can have bundles inside these IO blocks. Yeah, so it's a little bit of syntax breakdown. We've learned about bundles. So bundles are a way to aggregate, fields together. Um, the IO thing, now we know a little bit more about Scala, we can recognize this is going to be the apply method on an object called IO, right? And that's what it is. So it's like a factory method for bringing stuff in. Um, a week and a half ago, I think someone asked me why when we created instantiated modules, we needed to wrap it inside module when instantiating it. From a Scala point of view, you don't. But from a Chisel point of view, you need to. And the reason why is that module object context included various things for that module that's being instantiated. For example, when you instantiate a module, we don't normally think about it, but Chisel's doing things like connecting clocks for us. And so if you instantiate a Scala, as a module of a Scala class anywhere in your code, there's no context for it to know how to connect the clocks like that. But if you instantiate that inside that module helper function, then it knows where clocks are and stuff like that. And there's various other kind of things it needs to do to be a proper class. And so the choice made when designing Chisels, there's a few of these, companion object helper functions we're using to kind of encapsulate certain complexities. And, it's a little bit of a balance when you do an embedded DSL to try and make these things seem intuitive rather than like boilerplate. And so, yeah, so IO is kind of a way of doing that. Cool. Okay. And so that's kind of another thing to look into this. We did the queue in our last lecture. We got all the way up to V6 where it was, fully parameterized, really cool, except we had to have a uint as the type, right? And what we want is a generic, right? We want the ability to have not just a arbitrary with uint, but actually an arbitrary type in there, where there could be a uint, an estant, a bundle, whatever. And so Scala has that. It has that and more. So we're going to see that in the next slide. I kind of want to set the stage for it, right? So when you do a generic, in a lot of languages, you can just say, oh yeah, this is a type, whatever. Scala to do something called type bounds, where you can say not just whatever type, you can say a variety of things about the type. You can say things, there's a whole bunch of type theory available in the language. It's complicated, but at a high level, you can say things like, I want a type that is this type or a descendant of this type. So actually, you can put a constraint on that. And we'll see that in a second. There's even some cases where you can say, I want a type that's at least a parent of this class. Also possible. um, and there's a really quirky thing that's possible in Scala. It's called type erasure. And this is, I would say, by far my least favorite part of the language. That's why I put it on the slide. You go down this rabbit hole and read about this blog post. If you start writing Scala and you start writing generics, at some point you're gonna come across this. And when you run the compiler, you get this really cryptic message, and you go look in line and figure out what's going on. So this is, in my opinion, like the original sin kind of thing here. So what's going on? When you do generics in most languages, the code is written once. The type you're working on is templated, meaning whenever you instantiate that thing, it creates compiled code for each instance of that type, right? You know, if I instantiate with int versus uint, you get different code blocks. Great, cool. Scala by default does a poor job remembering which is which. And so this type erasure is that depending on how you're using generics, it will quote unquote lose which type you did this on. And so that blog post will tell you how there's a way to do a couple of imports and includes to actually make it pass around these type tags for you automatically to do the right thing. So you're wondering, why is this a optional feature to be turned on rather than like the default behavior? This is where I get grumpy. The reason why this problem exists actually is because it comes from Java. And the reason why it happens in Java is the person that made these choices in Java is the person that created Scala. So I disagree with the choices made here. So Marno Dersky was, a longtime Java developer before he made Scala in 2007. And so when Java added generics, now, not 20 years ago, but almost, they had a similar problem where they had people running JVMs that were older, and the JVMs they were running on didn't know about templated types. And so they made certain choices to allow people to write generic code and run it on older JVMs. And those choices have lived with us today. And now here we are in Scala talking about type erasure, which is, I think when Scala ran into this problem, it should just pass around type tags all the time, always, and never make this an issue. Marno Dersky chose not to because that was, a possible source of slowdown. Scala's already slow. And so, yeah, this slows down programmers figuring out what heck type erasure is. Okay, let's see this in practice. In code, like I said, type erasure only comes up when you're writing something with generic functions. A lot of times you can write a lot of generic functions and it'll never come up. You never even wonder what I'm talking about. Okay, so here we are templating on the type. So we're going to have something just passes through. And we're saying we are going to be something that inherits from Chisel data. What the heck is Chisel data? Here's a type hierarchy for Chisel, right? So you can see we have, like before, we have the internal types, which we should not be instantiating. We have the exposed types to the user. And then, users, of course, are also encouraged to make their own types. Like, of course, we often extend bundle, make your own custom bundles. And so turns out uint and sint are extremely similar, right? And so we can kind of take advantage of that. But at the end of the day, they're mapped something called, a data, right? We also are familiar with, bundles. We're familiar with vex. And so you're kind of saying, what else is there? Oh, yeah, there's a bool. We know about bools. There actually is a built-in type for fixed point in Chisel. We didn't cover that at all in this course, but there is. And yeah, maybe I'll pause for questions on this so far. Yes. Why does bool point to uint? Bool is a special case of uint that is 1 bit wide. Now, the better question is, why does it point to reset? And I believe a reset obviously would be implemented with bool, but why it needs its own type, I'm not sure. And you can see, for example, when you have both num and bits like this, we just said we can't do multiple inheritance. So we know at least one of these is a trait. I would suspect it's probably num because there's no parent, right? So this is probably a trait, and this is probably inheriting of like this. This is probably an abstract class, be my guess. But yeah, so for a lot of things, if you want to just have a templated chisel type, data's great, right? But maybe you know for sure you want just a number and you don't want someone giving you a vec or a bundle, then you say maybe bits, right? Um, so yeah, so it actually wasn't too scary, right? We had to do square brackets for the template type, and then we go ahead and use that type inside our argument list, right? So yeah, we go ahead and apply that type, um, and boom, we have a generic pass-through in this case. Now, as a reminder of what we're doing here, this is a little bit of that weirdness of having a embedded DSL. Uh, T is the type. So then what the heck is gen? So gen is a generator of that type, or what we think of as a type, right? So when we say something's a uint, we're actually talking about like a uint generator. That's why it's kind of being passed in like that. But if you're making your own generic chisel objects, you can just kind of somewhat copy the structure of this code and should hopefully be okay. Yes, question. If I don't have the type bound, this is what's called type bound, that should totally be okay unless we get type erasure. Oh, I don't think that works, right? There are different symbols you can put here, and I forget which one's which. Uh, you can look it up. There's a whole bunch of stuff about contravariant types and covariant types and upper bounds and lower bounds. But yeah, I believe that's the right symbol to put there. Yeah. It's saying that T must be uh, a child of Chisel 3 data. That's what the symbol is telling you, right? So if I tried to do this with something totally different, like an int, it's going to complain loudly because it doesn't match this type bound. So yeah, so I want a chisel type. That's what I'm saying. Hey, I want something that's actually chisel I have a chance to work with. Cool. Good questions. Cool. So then, of course, we can take. Yeah, go ahead. Oh, how are types implemented? Are types abstract classes? No, not necessarily. Types can be concrete. Normally, when you think of types in the Scala world, there's the built-in types, and then every other type is like a class you've like written or something. Uh, Chisel makes that a little confusing at times because we have these like type. Things like a uint or. But yeah, they are not required to be abstract. It's going to generate an instance. Yeah, cool. Okay. Um, so we can take our V6 code from last lecture, which was a Q, and now we make it V7. The only difference is we're just saying, hey, we need a uh, type. We take that as an argument, sure. And then, we instantiate our, memory. Of course, we do that. And that's all it takes. And then, boom, we took that thing, and now it is. We of course can run it if we want to. Now I templated Q, right? Um, so that's pretty cool, right? So between last lecture and this, a little bit of code right now, we've now built a pretty useful Q module, right? It's able to um, take in a non-power two number of entries. Its latency is based on how many things are in there. Bits only read or written once. There's not a lot of bit toggling. Incrementally built the way up to that. Now it's pretty generic. So I think this is a good pattern, right? When you're trying to build your projects, like we're talking about in a second, think simple, think small. What is the most reduced complexity I can build first? Get that working. Maybe we have less parameters, less flexibility, less generation, and then you kind of start incrementally adding it on and on and on and on. Cool. Okay, so then let's talk about the project then. Okay, so as pitched in the beginning of this course, this is going to be, we are currently doing a Lab 4 homework 4. Well, actually Lab 4 was due last night. There will be a Lab 5 homework 5 next week. There will be the week after, it'll be a Lab 6 with no homework. There will not be a homework 6. Okay, so for the remainder of the quarter after that, we'll be working on a project. Now, the project's kind of a really fun place, and it's kind of really self-directed in the sense of what's an exciting component for you to build, right? So um, the goal, of course, there's many goals educationally, right? But number one, you're actually going to get design your own chisel generator, but there's also some things we learned about in working the agile development process of okay, how do I start small and get something working, keep kind of augmenting and extending it. At some point, you're probably get big enough, you realize, oh wait, I need to do a big refactoring or big revision of some sorts. And as part of this project, you're also going to get a chance to embark on some more project-y kind of skills we didn't do in the homeworks. Maybe you want to set up your own continuous integration testing. Maybe you want to do a style check and that kind of stuff. You can do these various things. You can do code reviews. Up to you. In terms of what does it need to be, uh, the traditional model for this course is done in pairs. And when people ask me what's the complexity of what it should be, I say about 1.5 times the last homework problem. So next week we'll have another homework problem. I think honestly this week's homework problem was comparable complexity. So imagine like the Matt Mole MC we're doing right now for homework 4, 1.5x, for 2 people. Now, you're not required to work with a partner. Normally we say that because we have a lot of students. We've had few students this quarter. So we have enough class time. If people want to work individually, they're more than welcome to. Of course, that will scale the expectations for the project down to being less than a homework size problem, which is fine. Some students really get into it. So some students, we're telling them what the bar is, but they want to go way more sophisticated on their own because they find it really cool. That's awesome. Up to them, right? Do realize though that when we face homework problems, we as staff are doing a lot to try and what they call scaffold the problem in the sense that by giving you hopefully clear, although people have found various ambiguities, specifications. We give you some test cases. We give you some starter code. There's kind of some structure, right? And it's actually, believe it or not, is saving you a fair amount of time. When you're doing your own project, you're going to spend a good amount of time just trying to understand, okay, wait, what are the modules? Like, what does what? So like that other stuff, starting from scratch, takes a little bit more time than you might realize. But you can have fun with this, right? So if you go to the homepage, you can click around the project tab. And you can see I've linked to prior student projects that they've made their content public. Some not all of them are public, but some of them are. And you can see things vary. People have done things like cryptographic ciphers, encoders for LTE. One student did like the computational math behind GPS. We also have people doing some fun stuff. Last quarter was kind of funny where they saw, okay, wait, if you're doing a game of life, and that's kind of a funny thing. Or if I built a game of Snake in Chisel, okay, so they have like a Snake imitation in Chisel, and that's kind of fun. Or someone did like a fractal generator in Chisel. So like, even if it's a agile hardware class, if you want to make something that's like technically hardware, but you probably wouldn't build hardware that way, and it's more just kind of a fun simulation demonstration, I'm okay with that. So if you want to come talk to me in office hours about what projects make sense, or get some suggestions, we're happy to kind of pitch ideas if you need some. That sounds good. Also, of course, feel free to reach out to classmates or even use Slack if you're saying, hey, I'm interested in this, and anybody want to join me on this project or something. Like I said, so you can work alone, together, both are possible. In terms of how it's going to go, the rough timeline is so today I'm telling you about the project's existence. Next week, hopefully we can get more concrete in terms of ideas and what you want to do. Uh, on Monday, the week after that, so in other words, 10 days from now, you're going to get sent us a one-page project proposal. So that proposal is just a high-level thing, just kind of giving us, hey, I'm doing this alone. I'm working with so-and-so. Here's what we're going to do. And some of the key things we want to see in the proposal are things like not only what the final generator look like, but also how am I going to get started, right? Like what's the simplest thing you can build? What other code line can I reuse to make my life easier, right? For example, sometimes people say, oh, I'll write a Scala model. And it's like, that's great. How do you know your Scala model's right? Well, if you can find like a Python code is the exact same functionality, so we can check your Scala model, you gotta get bootstrap and get going, right? And so these are kind of all the questions we might want you to ask and explain your proposal. And the reason why you make the proposal is because during class time on that week, we are going to meet and discuss your proposal with you and give some feedback. Okay, have you guys considered this? Have you thought about this? Have you thought about this other thing? Or keep an eye on this other thing. And then, of course, you'll continue to work on the project. So our advice student says close the loop, right? Get something working, get something through tests, and kind of just keep adding functionality, adding more features, adding more flexibility. Um, there's going to be a deadline where we ask you to send us a link to a repo. And a repo should have something that does something. Doesn't need to be done. Just some sort of initial proof of concept is working, right? So like, read me, okay, do get clone, and then go into directory and do like make test or SBT test, and it's okay, something happened, right? And so it's okay if it's not complete. It's just we have this intermediate done to make sure you're making some progress. Because part of the goal of this project is just to get the end result, but also kind of appreciate the process, right? So in order to have a chance to revise, there needs to be something there in the first place, right? So then that's kind of the point as you start eventually kind of completing this project. And then in the last week of instruction, you're going to give a presentation to your classmates. I don't put the student presentations online, they're internal. We will send you feedback via email, and you can incorporate that. And then during finals week, you're going to turn in the PDFs of your slides. Now, if you're happy with your presentation and you feel that you don't, either we're going to give you a lot of feedback or you don't, you can turn the same slides in. But if you want to revise that, it's kind of an opportunity for you to kind of change your presentation to make sure you cover all the points. So for the most part, usually when it comes to the project reporting, the reporting is only via slides, not via any kind of write-up. When students lose points, usually it's only because there's lacking content. We give them a list of things to include, and sometimes they don't always include everything, and so that's why having the initial grade be during the presentation, but then give you a chance to revise it, you get some of those points back for the final grade of the class. Cool. Questions? Cool. Okay, and then, oh yeah, so here's the concrete dates. We just kind of talked about this, right? That, yeah, so you need to have a proposal, link to a working repo. Like I said, just because some of your prior classmates have done things publicly, we encourage that, but not required. Technically, all I need to do is make sure that Haoyuan and myself, GitHub accounts, can see your repo to give us, read permission if it's private. Then of course you present, and then Monday finals week the chance to send in the final repo and final presentation. Occasionally, there's situations where we have two class dates dedicated to. For example, we dedicated 2 LED days to presentations. We also dedicated 2 class periods to project meetings. Usually, how I do this is for the project feedback meetings, the early or proposal meetings, that's going to be random because I don't know who the groups are. That's why I asked for a little bit of time. I say I want them by noon on that day, so I have time to figure out the groups. So I'll like randomly assign some groups for that day, some groups for Wednesday after. And then when it comes to presentation time, I swap the days. So if you were on the first day of proposals, you're going to be the second day on the, or vice versa. And remember, when you're presenting, it doesn't necessarily need to be your completely completed product, right? You still have a few more days to revise and make the final presentation. But as your in-person presentation to your classmates, it's kind of fun to see what else is working on. Cool. Other questions? So yeah, so here we are. I know we're winding down. I'm making the final plans for the last few lectures. There will be at least 1, maybe 2 guest lectures. So I can tell you a week from today, there'll be none other than Professor Jose Renal talking about pyrope. So it'll be kind of a fun contrast. So all quarter, if you hear me get on this, campaign to get you all writing Chisel and, teach a controversy, teach the other side. So let Jose talk about pyrope. And that'll be good. So those unfamiliar with pyrope, Jose's working in this language for quite some years. He's had a number of students do some really cool work on it. If you haven't heard about it, it's not a secret. Sorry, not an accident. Jose's kind of kept it not fully public because he's still working on it. But there's been a lot of cool internal versions of it, some really neat features in that language. One of the most interesting things that might come apparent to you. So all quarter, I've been talking about Chisel and pointing out how Chisel's embedded in Scala. So kind of about these certain things in the language where if you're designing a language from scratch, you wouldn't do it that way because you just have the construct. But the advantage of embedding language is, of course, very easy to implement, right? I don't need to invent a language. I just need to invent a library and put in an existing language. Pyro was actually its own native language. There's no embedding. So it has its own parser and all that kind of stuff. And so you'll see there's a lot of things by virtue of being your own language you get right. But also for him developing this language in this group, it's a lot more complexity because it's not an embedded DSL. So there's a trade-off there. There's kind of plus and minuses both. And Jose and I collaborate research all the time. We're always like, oh, that's the advantage of this, that's the advantage of that. So we've now through this for a few years, we've seen there's like a list of features that are pros and cons of both embedded versus standalone native languages. There's kind of both have their cases. And so that's why I was kind of eager to get him to speak up about pyrope because that one is, a in-house native language. If you go digging through the prior course offerings, you can see a few other guest lectures from the other languages. I believe in the first offering of this course, I got Tim Sherwood talking about PyRTL, like a Python-based one. It's pretty fun. There's been a few different languages out there over the years. Cool. Anything else? All right. Well, have a good weekend, folks. That's all.